Screw up this integral in front of everyone, you're all going to think I'm a dumbass. More so than perhaps usual. I'm going to go close the door so I'm allowed to swear.
Calculator this time?
I do! No, actually, we don't need calculators today because we're going to get integrating. Maybe. I don't know. I don't think I put any numbers in anything today. No, I did. The last question. You're right. Thank you so much. Hi, Jane. Hi, Bestie. Physics? Physics lecture? No, go upstairs, middle of the floor up ahead. All right. Every time someone's in here. All right, so let's take a look. Banging. Some people have tried some questions. Some people have not tried some questions. I appreciate you. Okay. Good. All right. So far, no one said anything mean. Appreciate all of you. Hello. Physics time. Let's go. Where's Tarek? Oh, Tarek, there you are. Sorry, you weren't in your usual spot. You're the only student whose name I remember. So, sorry. Sorry? No. It's fine. You know, like, I don't know if you've ever lectured before. Actually, by definition, no. But yeah, you have like students that you remember the name of sometimes. All right, so let's get started. Okay. So it's time. We're doing the real shit today. Fellas, what's up?
We just want to get close, you know.
Oh, good. Okay, I thought you were leaving. Like as soon as the lecture started, and I was like, what? What have we done? All right. So
Never do that.
yeah. All right. So today is the first lecture where shit gets real. All right. We're gonna do an actual useful problem, and we're gonna do some actual maths, and we're gonna do some integrals, and more specifically, we're gonna do what physicists love to do with integrals, which is to minimize the amount of work we have to do. Okay. The way to succeed at mathematics in physics is to know all the tricks you can do to get out of doing it. All right, and that's what we're going to be teaching you today. We're going to be slower and more methodical. That's the word. And luckily for me, the important stuff is in the front half of this. Now, thank you everyone who put in their... Did I put the questions in? Yeah, I did. Excellent. Thank you to everyone who put their answers in for this. I'm going to go back because it's doing this thing again where it's, you know, I press it and two hours later it does. Right? Today, the principal aims are to be able to do electric fields for shapes. Okay? So for objects that are not just single point charges. The second is to have confidence in doing integrals. That's why I asked you if you're confident on integrals. If you aren't confident, don't worry, neither am I. So we're going to figure this shit out together. And third is to learn what flux is. And the reason for that is because flux is an important topic for next week where we do Gauss's law. And Gauss's law is the GOAT because it lets us get out of doing integrals. All right? It's just easier. We don't have to do integrals for first year for Gauss's law. So it's going to be GOATed. All right. Now, people who filled in the form, I appreciate you. The most common thing that people didn't understand was what the hell is a dipole and what's a dipole moment and a few other things. So dipoles show up in the second half of this lecture. And so in the second half of this lecture, I will spend a bit of extra time and we'll do a bit of dipole revision. Okay? But that's later. For now, we'll focus on electric fields. One thing I really liked was someone was talking about how, well, with a dipole, right? We have like Q and minus Q. And we have here the distance is A, right? The distance between them. And if we have R, the distance that you are, being much, much bigger than A, well then don't those two dipoles effectively look like they're on top of each other? And the answer is absolutely yes, but not according to the test, okay? Because the distinction R greater, greater, greater A is, you'll learn the difference between assuming this is true and this isn't true next week, all right? Because we do dipoles where that assumption is not true, and we do dipoles where that assumption is true. But in both cases, it's still a dipole formula. It still doesn't cancel out. And yes, theoretically, it should frickin' be 0, right? Because if R is sufficiently large compared to A, then yeah, they overlap. But I'm telling you for exams, all right, they didn't put a trivial question like that in. I'm sorry, right? But it is a very, in my opinion, logically correct assumption to make, right? That if you're far enough away from this dipole, it shouldn't look like a dipole. But we're contrasting it to the case where the electric field of this one and the electric field of this one have the shape of the dipole being relevant. And we'll get there, right? So for now, your mind is correct, but not the same train of thought as the person who wrote the question. And so unfortunately, that's the brain we've got to be having. Come on in, besties. Let's go. So, the key things to remember from last lesson are these two. That the electric field from some charge, Q, at some distance r, is this doodad. Q over 4 pi epsilon naught, r squared on the bottom, and r hat. Remember, r hat meaning in the direction of r. And we also need to remember that electric fields from different charges will add together. So if you put two charges in space, the electric field at any given point is the electric field from charge 1 at that point, plus the electric field at charge 2 from that point, but it is a vector sum. Okay? It's not just the magnitudes added together, and this is where we encounter difficulties. And you may be dreading a scenario like this. This is what we're going to attempt to solve in the first half of today's lesson. This is my goal. If you can get this, there is a lot of extra stuff in the first half of today's lesson, but that's stuff that you can read and go, yep, okay. The stuff that I want you to be able to do after this lecture is, for example, a horizontal rod, one-dimensional object, has a length of L and a total charge of Q. What is the electric field at this point due to that entire rod? Of course, you do not know how to solve this, but it, sorry?
You had to add all the electric field for like you need to separately.
Correct. What we're going to do is we could do, the electric field for this part, and this part, and this part, and this part, and that's exactly what we're going to do. We're going to break it up into small parts, and we're going to integrate it. And that's why we're doing integrals today. Very good, very astute, everyone. But to begin with, we have to talk about how charges go on objects. And so we're going to start with yet another question. I'm going to figure out, hang on, room control, yeah, freeze image. Look, I even put a note for myself, Tom, freeze screen, right? If that rod, I'll go back, has a charge of Q, and let's say I say it's a conductor, how are the charges distributed along that conductor? That is our question. Oh, you're so ahead, bestie. Very correct, right? Appreciate it. So let's say, right, I have a sphere, and this sphere is a conductor, and I've shoved a bunch of positive charges on it. I want you to tell me, by following the code, and I'll put this up again, we go to, if you remember, ecopole.au, and then the code that we would join with is PhysicsGang. No space. I can spell PhysicsGang, right? How do the charges, when they are placed on the sphere, distribute themselves, assuming the sphere is a conductor? And recall, on a conductor, the charges can move as freely as they like. And also recall, in the words of Jean-Paul Sartre, hell is other people, right? You are all not behaving very well like charges because I see a lot more people sitting together than they were last time. Good on you, right? But what will these charges do? How will they behave? Now, of course, I haven't told you how they'll behave yet, so this is like a guess, right? Or you might know, right? But we'll see. And while we see, I'm going to decide how much ramble I'm going to do. Okay. For a dipole moment? Oh, yeah. So the way that we derive the field for a dipole moment is literally just doing one charge plus the other charge and then doing some maths. But the derivation doesn't show up in examinable material, so I'm making kind of decisions as to what I show the derivations for and what I don't. But that's absolutely correct. You just superimpose the two. And originally I actually did have the derivation in my slides, and then I was like, oh shit, no time. Let's see how we did, besties. Good distraction question too, because that gave everyone time. They distribute themselves equally along the surface, or they distribute themselves equally throughout the volume. I love that everyone, I love that everyone realized that the spheres distribute themselves in some form of homogeneous shape. And would anyone who correctly identified B, that they're on the surface of the sphere, care to explain why? Why are they on the surface of the sphere, Bestie?
Because if you've got a particle, like they want to be as far away as possible.
Yeah?
And in that case, you can't have a particle in the middle because it'll get pushed towards one of the sides.
That's a really good way of explaining it. This was correct. Anyone who's also eager, over here.
They get as far away as possible from each other.
Yes, yes. Correct, same. Were you going to say the same thing? Ooh, I love that one. We're going to go to that later. Very good. All right, love it, love it, love it. Here's a general rule. Charges always distribute themselves along the surface of a conductor. Why? Every explanation is valid. It doesn't, none of those explanations is more correct than any other because all of them are correct explanations for why this happens, right? So you could say they want to maximize the distance between themselves and every other charge. If you put a charge in the middle, right, that would mean that it's really, really close to a bunch of other charges. We could also say, and we will learn later, that the electric field inside a conductor must be zero. All right, and we haven't learnt that yet, but we will. And that means that there can't be just one charge chilling out in the middle because then it's going to be radiating its own electric field. So however you choose to know it, it is a fact that conductors are functionally a shell, right? The charges always distribute themselves homogeneously along the surface of a conductor. And what this means is that we can express charge on a conductor as a charge density. Now, we could also do it for a non-conductor, but it's way more complicated because they don't distribute themselves, right? They'll just stay wherever you put them. So screw that. We'll do that later. All right? We can express charge as some form of charge divided by something. Charge per meter squared, charge per meter cubed. And that's what, and remember, double red line, so those are the important statements, right? My boss told me, Tom, make sure you remind them about what the color of the slides means, right? Because that's good. My boss, very smart, boss Dr. Kate Jackson. Shout out to Kate, right? Kate the goat. If we have our charges distributed in a shape, there's three ways we express it. If they're spread out in a one dimension, we refer to that density as lambda. You might recall lambda from the mass density, right? Of like a rod that you had the moment of inertia of. Hopefully triggering some flashbacks, right? So it's charge. Why did I put newtons? Am I some kind of dumbass? Don't answer that, please. It's coulombs per meter, not newtons per meter. I'm so stupid. I don't know how I didn't notice that. Anyway, whatever. It's coulombs per meter, or coulombs per meter squared, or coulombs per meter cubed. All three of these are called density. Okay? Now you could call one of them linear density, and you could call this one surface or area density, and you could call this one volume density. But what I want you to notice is that the symbol, which is either lambda, sigma, or rho, is equal to charge divided by the relevant shape parameter, be it length, area, or volume. And this is important because we will use this relationship to do some integrals, or more specifically, some variable substitutions for our integrals. Okay. So let's try some examples. It turns out we did need a calculator for the class. Nice work, everyone. Who brought your calculators? Bad work, me. So let's try a couple of examples. Let's try. This rod has a length of 10 centimeters. You keep it. I will suffer, right? This rod has a length of 10 centimeters and a charge of 1.73 microcoulombs. What is the charge density? Well, we go lambda is equal to Q over L, because this is a one-dimensional object. It's a rod. And so that's going to be equal to 17.3 times 10 to the minus 6 coulombs divided by 0.1, right? Because we have always used meters. SI units. And it turns out, okay, you don't need a calculator for that one. That's 17.3 times 10 to the minus 5 coulombs per meter. Oh, it's okay, it's okay. I enjoy the theater of suffering, right? But yes, I appreciate all of you who are here helping me out. It is supposed to be me helping you out, but of course, I'm a mess. That's a joke. I've got my life together. That's on the record. I keep forgetting these are recorded, so I can't be like as dumb as I'd like to be. So, let's try another one. A disc has a radius of 5 millimeters, and maybe I'll even change the pen color to match. That'd be gangster, wouldn't it? Can you see the purple? No, it sucks. All right, back to yellow. Back to yellow? Oh, no, it's gone to next slide. Thank you. Thank you, projector. I love you so much. Okay, there we go. So, we're going to do, what are we going to do? Sigma, lambda, or rho? Sigma, very good. Sigma is equal to charge over area, which is 4.23 times 10 to the 5 microcoulombs, so that's times 10 to the minus 6, right? Works out. Divided by the area, which is pi r squared. Pi times the radius, which is 0.05. I trust you. I would literally put 5 times 10 to the minus 3 in my calculator because I do not trust me. Squared. Anyone got that for us? 0.005. Oh God, really? Really? That's pretty cool. Is it about that? Bessie's in the middle? Oh, it should be 0.05 there. Oh, whoops. All right. So 5 millimeters, yeah, it should be 0.005. Yeah, you're right, because 1, 0, that's 5 centimeters. Look, when you get up in front of a crowd, your critical thinking just leaves, right? It's all about the performance. Any calculator besties in the audience? Tarek, did your back hurt from last class carrying it? No? All right, good. I learned that joke from League of Legends. Don't play League of Legends, kids. It's bad for you. All right. Anyone got a number? 5,385. 5,385 what? Coulombs per meter squared. Very good. Very simple calculation. Okay? If you got a different number, you're also correct. I didn't calculate it myself. Sorry. But I want to ask you, what shape are each of these? Okay, so if I were to ask you for the charge density of a line of charge, what symbol would you use? Lambda, very good. All right, how about a ring of charge? Also lambda, because it's a one-dimensional object. The charges can only spread themselves out along a single line, even though it is in two-dimensional space, and we'll get to how to do that maths later. All right? But the charges themselves spread out along a line. How about a thin disk? Sigma, right? How about a thick disk? Sigma, if it's a conductor, because it would be on areas, and rho, if it's not a conductor, because it would be through the volume. Same for a sphere, right? If you've got a sphere, it's only the area, the surface area that matters if it's a conductor. But it's the volume that matters if it's a sphere. The questions will make it explicitly clear, and we will not do any examples in this class that are hard. We will do line twice, okay? And the techniques we learn for line will work for ring, and they will probably work for disk, and then sphere, but thick disk maybe not, right? What we like are shapes that you can get through in one integral. Question? Yeah, so if you have a 3D shape that's a conductor, the charges are always distributed on the surface, and therefore the volume has no use. Sorry? Yeah. A one-dimensional shape, it's just one-dimensional always, right? So we don't have to worry about that, thankfully. So this brings us back to the question, well, how can we find the electric field? That's what our goal was today, right? And I have a whole half hour to do this, so I'm very pleased. Question?
In the 2D situation when it's a disk,
Yeah.
how do the charges spread themselves to the perimeter?
Oh, that is a good question. So, in a 2D scenario, if it's a thin disk, would the charges simply exist along the ring? No, you're right. That might actually be how it goes. Don't know. I'll have to try it. Yeah, because it would similar to be a ring, because you're right. If there was a charge here, ooh. Yeah. Okay. Ambiguous? Don't worry, that sort of stuff isn't going to be in an exam, right? I've done every question. There's no ambiguous question like that, but that is a very good question, right? And I think it speaks to the limit of whether or not, like, what a thin disk is, right? Because a disk, in reality, has to have some sort of thickness to it, right? And then the charges can distribute on the top and the bottom of the disk. But an infinitely thin disk, some theoretical object, that is a very interesting question. Oh, crap. And I was supposed to look up skin effect for someone too. I'm terrible. I'm sorry. Right? But that's a really good question. Right? And one thing that's really important about physics, right, is you have to be comfortable not knowing shit. Right? Like me. Right? There's a lot of stuff you'll ask me. I don't know. We can figure it out. It's a good thing to think about. Right? But my goal is that you'll never have any I don't knows about the relevant, accessible things. Okay? But that's a very good question. Thank you. What was your name? James. Okay, I've got two names now. James and Tarek. Those are the two names I remember. All right. Sorry? Sofat. How do I spell that? Sofat. Oh, I thought you were saying your name was Sofat or something. I was like, oh no. All right. So, we got a charge density now. We're going to call it charge density lambda instead of charge Q. Does that help us? Well, presumably, otherwise why would I do it, right? Why would I bring this up? Well, let's talk about it. How are we going to do it? We're going to, as I think one of you two said, right? We're going to take our object and we're going to pretend it's a series of small charges. Now, you can take the rod and you can pretend it's one charge at the front, one charge at the back. That wouldn't be very good. So you go, all right, maybe 4 charges, right? We could do 1, 2, 3, 4. That's better. Or this many, however many that is, 8? I don't know, I can't count, right? But what we really want to do is we want to break it down into infinitely many charges. Each of these charges is an infinitesimal charge element. Now when we call something a little small increment that we're going to add together, it is d something. So this is dq, a little charge. And what we're going to want to do is have some sort of relationship where E is the integral of some stuff, dq. So add up all the little electric fields together. That's our goal. Question? Exactly correct. How this is going to work is every dq is going to have some formula for its dE, its little electric field. And what we're going to do is we're going to figure out, first of all, what is the electric field due to some arbitrary dq. So some formula that works for all of them. And then we're going to integrate that formula to find the total electric field. And that will work for every case. The only difficulty is how hard that integral is. So we're going to start with the easiest one, okay? Which is a charge along a line, so a charged rod, I guess, and we're being asked for the electric field just at the edge of it, okay, along its axis. This is the easiest case, okay? And the first thing we realize is that the electric field due to a charge element is just the Coulomb's law of that charge element. Remember, the electric field was just 1 over 4 pi epsilon naught, or Coulomb's constant, because some of the questions, they ask you to use K, and some of the questions ask you to use 1 over 4 pi epsilon naught, and it's horrifyingly inconsistent, and I'm sorry, but it tells you in the question, okay? It tells you to use K or 1 over 4 pi epsilon naught. If you use the wrong one and you lose marks in the exam, just tell me and I'll try to change your marks, okay? Right? If it's the exact same answer but you used 1 over 4 pi epsilon naught instead of K, I gotcha. I hope. Right? I'm legally not allowed to make that decision, but I'm hoping. All right? So, we have just taken Coulomb's law, and literally all we did was we put a D in front of the E and a D in front of the Q. So what we're saying is, for any tiny little bit of charge, you would get a tiny little bit of electric field given by this formula. And so our goal to find this final total electric field is 1, convert this formula into some form we can integrate, and 2, integrate it, right? And those two techniques, that's physics, right? You've already got this formula, now you've got to go, well, this is true for every single shape, right? This formula is always true. It's how you do the conversions, how you do the integral that changes. And so we're going to start with this easiest case. The first thing we're going to do is we're going to look at our 3 rules, right? This is the first, I think, ever yellow slide, the strategy slides. These ones show up mainly when I'm trying to give you a generalized solution, because you are going to have to do these integrals for lots of different shapes. One of them is for an arc, maybe for a circle, lots of different stuff. And so I tried my best to generalize the advice. So our stage 1 is to make this something we could integrate. And it depends on what shape of charge distribution. The first thing you need to do, and we will do this together as an example, right, is take dq and convert it into some kind of dx, dy, dA, dv, d something physical, right? Some kind of length or area or volume element, right? Using rho, lambda, and p. Now, if the question does not give you rho, lambda, and p, you can make it up, okay? You can insert any variable you want as long as it's gone by the end, right? And what we'll see is we can introduce a lambda, maths, and then it goes away at the end, and we're all good, okay? You can always do that. That's going to be very relevant for Gauss's law next week, right? You can always introduce a variable as long as it goes away by the time you submit. Then we've got to take r squared, and we've got to express r squared, which is the distance between the element we're talking about and the location we're talking about, the final location, in some form of variable present. And then we've got to take the direction into account. We've got to split it into the required coordinate system. Now, this might not make much sense to you, but we're going to do this together first of all, okay? We're going to take that previous example. We've got this formula. We've got this example. And what I'm looking for is to set it up so that I can integrate it. And when we want to integrate it, what we want is every single variable should either be the variable we are integrating over or constant. That's what we're looking for. So for example, in this case, r represents the distance between our little element of charge and our final, the location we're being asked for. R is not constant. It depends on which little bit of the rod you're talking about, and therefore we have to get rid of it, right? Because what we want is every variable to be a constant. K is a constant, so it's fine. Or the variable we're integrating over. So step 1, take dq and convert it into a length, area, or volume element. So what we do is we picture, okay, we're going to define x as the distance from the end of the rod. Now you can make whatever definition you want. In the exam, it will tell you the specific definition to make, and maybe it's this one. Who knows? Okay? But you could define x as starting from the middle if you wanted to. You could define it as the other end if you wanted to. It will get you the same answer. Okay? It should. That's how maths is going to work. So we're going to define x as starting from here. So this is our... Please work. What? Why? Sorry. There we go. We're going to define x... x equals 0 at the starting point. Okay? And we want to imagine this little element of charge in terms of x. So we realize that lambda is the charge density. So if you take a given length and you multiply it by lambda, that's how much charge there is. Because remember, lambda is charge per length. So what we do is we decide that dq equals lambda dx. That is our first substitution. Now you may do at some point dq equals sigma dA, right? Because you're doing little increments of area. Or you could be doing little increments of volume. But the most common one is dq equals lambda dx. All right, an element of charge is simply the charge density multiplied by an element of length. Next, we need to express r squared in terms of the variables present. So let's assume we are at this position here, right? We're at this charge element. R refers to the distance between our charge element and wherever the fuck it is we're talking about, wherever the hell it is we're talking about, right? So what is that distance? Expressed in terms of the variables we have here. If this whole distance is r, it's a plus x. That's it. We say r equals a plus x, or r squared is what we want, right? So we have r's. It's frozen again? Oh, I know, right? I think there's a button on this pen, right? So r squared equals a squared plus, shit, no it doesn't. A plus x all squared. Whoa, I almost screwed us up there. Woo! The next one does that though, all right? And then we take r, the hat r, the direction of r, and we put it in our desired coordinate system. So, if x is this way, right? R has a specific direction in the xy coordinate frame for us. Now, would anyone be surprised if the axis R and the axis X are the same axis? Right? Because R is along the x-axis, isn't it? However, I will note for this question, X is going to the right, but R is going to point that way to the left. Because if our charge element here, I'm going to change color just to do some more drawing. We'll use blue. If this charge element here is emitting an electric field, right, that electric field is pointing left, but X points right. And therefore, when we do the direction, we say that R hat equals minus X hat, right? Except we don't write X hat, do we? We write I hat, right? Because remember, I, J, K is X, Y, Z direction. Question?
So we make the assumption that the charge on the rod is positive?
Are we making the assumption that the charge on the rod is positive? Not necessarily. Oh, okay. Yes, because if it's negative, dq is negative, and then the direction flips from our vectors. So yes, this is the definition assuming a positive charge. If it's a negative charge, then when you do the integral, the direction flips itself. So we don't need to worry. This is one of those things where the maths does the thinking for us. We don't have to worry, oh, is it the right direction or not? No, whatever. Trust the integral, right? Believe in the integral. So we're going to combine everything, okay? The electric field due to one of these elements is equal to a constant, cool, times lambda dx, that's our first, we converted, dq, divided by x squared plus a, I did it again, x plus a all squared, right? Because x plus a is equal to r, and then we square the whole thing. And then, what? Go away. Good. Then, a minus out the front, because the direction is minus, in the I direction, minus I. So this is our formula. Now, the most important thing for you to do, don't look at me like that, bestie. I believe in you, okay? Yeah. Oh, okay. Well, don't drink this water, it'll kill you. The most important thing to do when you go home is, as soon as you find one of these questions, do it as slowly as you possibly can. You only need to go fast in the exam, and trust me, when you do it a couple times, working through it methodically, and you get it right, it feels great. I almost swore again there. Anyway, we'll continue on, all right? So what we want to do, we've got our formula for dE. Now we want to just find the whole electric field. So all we do is we integrate. We sum up each of those little electric fields into one big electric field. Okay? Now, an aside. This will show up in an exam. Double red. we have just done a one-dimensional problem. When you do a two-dimensional problem, just treat it as two one-dimensional problems. Integrate all the x shit, integrate all the y shit, integrate all the z shit. All right? If you get a two-dimensional problem, you just extract the x component of dE, the y component of dE, and the z component of dE. You do not need to do any bullcrap with angles. All right? Just do x, y, z. There's almost no cases where you have all three, and some cases that look like they have two might just have one. Okay? But you just divide and conquer. You do not do it as some big complicated integral. It's too much. Okay? So we express dE as separate equations for each axis. So if we had like a sphere or something, right? We'd have to do dE in the x direction, dE in the y direction, dE in the z direction. Question? You could do the three-step process for each axis, or what I would do is do the first two stages. I'll go back twice. I would do the first two stages once, and then split it up into x, y, z at the end. Because you can find the total electric field, dE, and then you split it up into x, y, z at the third stage. That's what I would recommend. Otherwise, you're doing a bit too much work. But there will be questions where it's faster to do it your way first. And we'll see one, actually, a little later. Okay. So then you use the question information to find the limits. All right? So integrate from somewhere to somewhere. Then you solve the integral. So we're going to do one. Are we ready? Here it is. This was the formula we hopefully had last time. Minus k lambda. What a little idiot. dq. Wait, shit. dx. I just typed this. Minus k lambda dx over x plus a squared I hat. We want to find e. So we're going to do e, I don't know if you know this, is the integral of dE. Wow, that's how integrals work. Of course. So it's the integral of k lambda dx over x plus a all squared in the I direction, and there's a negative sign there. Question? I'm about to do that. Exactly correct, right? So this integral is not infinite. We start here at x equals 0. What was your name? Malloy. All right, thank you, Malloy. We start here at x equals 0, and we end here at where? X equals? L. Remember, we said the rod had a length of L. Did I put it in this picture? No, because I'm a terrible person. All right? And this is where your decisions matter. Because you could have picked x equals 0 in the middle. Then your integral would be minus L over 2 to L over 2. You could have picked x equals 0 at the end. Then your integral would be minus L all the way to 0, right? Your choice of coordinate system affects your integral limits. Question?
Are there cases when choosing L in the middle is better?
Yes, and we will see one right after this. Question was, sorry for the audience, is there a case where choosing x equals 0 in the middle is better? Absolutely. And it'll be the case where they ask you for the electric field directly above the middle. Question? Yeah. Yes, exactly correct. That's exactly what we're going to do. Yeah, don't worry about it. 100%. I'm so happy you're already thinking like this. All right? Will we have time to do it? Maybe. Maybe I'll make a video. I'll probably make a video going through it, okay? Because I want us to make sure we at least do one properly without rushing. But I'll make a video on the second one. Anyway, it's time to do this integral, right? Because this is it. We set up the whole integral. Now we just got to integrate it. All right. So what do? Well, we put all the constants out the front. So we get minus k lambda integral between 0 and L. I'm just going to write 0 and L instead of x equals 0 and L of dx. Oh, actually, what we'll do is we'll write it as x plus a to the minus 2, because that's 1 over dx. And it turns out that integral is actually really easy, right? It is. No, I know what it is. Don't worry, I was doing that for effect. Minus k lambda, and then this integral becomes x plus a to the minus 1 times minus 1, technically divided by minus 1, but that's the same thing, right? Between 0 and L in the I direction. Then what you would do is you would do your standard substitution. You would put L in, and you would put x equals L in, and you would subtract x equals 0. So you do, okay, minus k lambda. Sorry, this is going down here. Oh, I'll go back to yellow. Will I, without screwing everything up? Okay. We did it! Minus k lambda. And then it's going to be negative L plus a minus negative 0 minus a. And those are both to the negative 1, right? Then you algebra it out, whatever, okay? The answer algebraically becomes, right? Where can I write this? I'm going to write this up the top here. Why? The answer becomes minus k lambda L over L plus a all multiplied by a. And then importantly, we made lambda up, but lambda times length is charge. So that becomes minus kq over that denominator bullshit. Denominator stuff. All right? Now, there's a little bit of algebra-ing to get there, and the answer looks ugly. Don't worry. Every answer looks ugly in this course. Okay? There's no pretty answers. The important part was the setting up and the solving of the integral, and then the rest of it you just kind of algebra together. Okay? The good part about the question, the quiz, is that it can evaluate whether or not two expressions are algebraically the same, and therefore you don't have to worry about algebraically reducing it, right? Once you get an answer with the correct variables in it, you just shove it in there and it'll give you the right mark, right? You don't have to worry about, for example, in this other integral we'll do, there'll be an L over 2, but we could have defined it as L and it goes from 0 to 2L and all this other shit, right? Doesn't matter. What matters is that you get the right variables, so you get rid of your dq's and you get rid of your dx's and you get rid of your lambdas. Unless the question asks you to keep lambda, then you keep lambda. Read the question. Oh my God. But you do the substitution for dE, you do the integration of dE. That is the idea. Now what I would like to do, right, is do another one. Do we have the time to do another one? No. Will I make a video of me doing another one for you? Yes. Okay? But before I talk about it, right, I want to go through some strategies, okay? And this is particularly relevant for the next one. Look for symmetry. Can you just integrate for half of it and double your answer, right? Like what if it's symmetrical, right? Look for canceling components. As, what's your name, My Chemical Romance guy? Siddhan? Sid. As Sid said, when we're doing, let's say, the electric field at the exact center above a rod, well then, there's a little bit pushing to the right from this end. There's a little bit pushing to the left from this end. Everything okay? We slaying? All right. Oh, if there's questions, you can yell, right? This is physics 1B, right? No. Hold on. Where are you supposed to be? Are you supposed to be in your OTH class? Oh, no, Misty. Oh, no. This is the lecture. Okay, it's okay. There's another one running at 4 till 6. Okay, it's okay. I wrote them. I can run you through. Okay, this is the course after your course. Yeah. It's okay. I'm in charge of all of those classes, all right? Yeah, it's okay. I'm so sorry. Yeah. So after this lecture, I'll go take you to the class to get your book that you need to get, and I'll explain everything to you, okay? Yeah, don't sweat it. I run all those classes, so don't sweat it. I'm important. Sorry? This is for, what degree are you doing? You will never have to do this. I don't know why you're here. This is for electrical engineers. Yeah, okay, don't sweat it. Hey, look, physics is cool. Yeah, you don't have to stay if you don't want to. You can come back here at 4, and I will take you to, like, I'll get you your book and stuff. 4. All right. That's the funniest shit I've ever seen. All right. Love it, love it. My apologies, bestie. Did you go to the other physics lectures at least? You did? That's the best part. Did you go to another one that was just here? Like today, right? Like an hour ago, right? Beautiful. Beautiful. All right, no, don't. That's the best, bestie. That's so funny. All right, everyone? So, anyone got tips? During the break, everyone tell our new best friend tips to pass 1A. All right? That's what we'll do. Anyway, sorry. Look for components that cancel out. Yeah, whatever. The third thing is, some of them, it'll look like, shit, I don't know how to solve this integral. There's standard integrals in the formula sheet. Use them. All right? So the example I'd like to go through was this one. Okay? We don't have the time for that, unfortunately. Right? But I'll make a video. I just got my new writing tablet, so I'll make a video. Oh, my PC components just arrived. Maybe I'll construct my PC and then play League of Legends.
Is that going to be a video as well?
Sorry?
Is that going to be a video as well?
No, because it'll be me swearing like a lot. I got my new parts because I broke the old parts installing a new fan, all right? Clearly me and technology, we're not the best friends. Anyway, so what we would do is we wanted to do this one, and we do the same rule, right? We go, okay, we have like some charge element dq, and we have this r is now this vector. It's different, right? It's harder, right? And then we go, okay, well, you know, dE equals k dq over r squared r hat, and we do the same 3 steps, and so on and so on, but we don't have the time. I'll make a video for it. Question?
So then over here we take x equals 0 in the middle, right?
Yeah, we take x equals 0 in the middle.
So then r is root of a squared plus x.
Correct. And then essentially what you do is you get this integral that's x squared plus a squared to the 3 over 2 with an a on the top of it, and then that integral is a standard integral, right? Stuff works, believe me, all right? It works out. Anyway, we'll skip it. New thing time. Okay, tell you what. We'll actually use this as our break time because all we've got next is ramble. So we'll use this as our break. We'll take a break until 3 o'clock. All right? And then we're going to learn. Basically, that was the only hard math thing today. That was it. The rest of it is learning new formulas that you can just use or learning about a new concept called flux. Okay? So we'll take 10 minutes. We'll take a break until 3. Yeah. All right, we're done. Until 3. Big break. All right, bestie. Killing it. Good on you. Anyone have any tips for bestie on 1A? Who passed 1A? By definition, all of us.
Yeah,
absolutely right. The way we get around it is we simply don't do charging investing.
We do like the other one, like some signal.
Some, but also quantum and charge aren't joined as much as you think. So so when we do EMAG here,
Charge is like spin. It's like the orientation of all the spins, electrons and shit, and like they can have quantum interaction of the electromagnetic field.
that's not an incorrect thing, but I don't know a good enough way of saying it that won't wind up wrong. So I'm going to say no, right?
That's exciting.
Yes. It is, but you have to understand, of all the fields that exist, my weakest is quantum. So quantum was my worst. I did get a PhD in it, but like in terms of understanding, right, was my worst by far. And my PhD was entirely in non-quantum physics. Partially for the reason that I'm not very quantum. But I will ask, because there are several quantum, I'll actually ask Rajib, the same guy, because he does quantum computing as well. But the prime perturbation will be to second year electromag is like first year electromag, conceptually just half shapes. Cool. And then third year is relativity plus electromag.
Oh,
Relativistic
that's
electromag. It is cursed.
That sounds
It's
amazing.
so cursed.
That sounds like a lot of fun.
So if you travel at the speed, so for example, you know how a charge moving in a magnetic field, right? It experiences force. What if
It was moving like in the LHC at like 80% of
that exactly? But like, what about relative velocity? What if you are moving alongside the charge, and therefore you do not perceive the charge as moving? Einstein's theory of relativity says that we should
the
not be
force
able
of
to
physics should be the same.
exactly. So what changes? The perception of the magnetic field.
And that's I mean messing with like what we want the space time is
It is so
so
that's
much
the
fun
idea.
though.
A relative similar to that. I'm going to get to the next question.
Yeah.
So thank you, Marcus. I really appreciate it. All right. James.
Yes, I was supposed to be emailing you about next working over the lab manual stuff.
Yeah, sure.
But do I need a post here? Because I know
I'll give one to you.
is there one? Because I got the lab manual.
We'll give one to you.
I got the lab manual.
Yeah, we give you the.
Okay. Sweet.
Right. Awesome. What are good questions? Taking a nap, Bestie? I love napping.
Wait, one second. Because I won't be here for the tech. I just do it in my videos.
I'll level with you. A lot of students find the OT too easy.
Yes.
So you take a look at it and decide if it's worth it.
Oh, so this is
It's not mandatory. It's not mandatory. It's not last. The only things that are last are those tests, weeks 3, 5, 8, 10, and the labs. Okay? So you decide if it's worth your while. They do work you up.
Yeah.
So that's what I like about them, is that it's designed for the people who honestly need the help with learning, which is kind of who you should be targeting for the majority of courses, is the people who need help to understand stuff. Right? At least that's my vibe on it. Because we have other courses for like the advanced, where it's like, okay, the assumption is that you study a lot. And then these courses are for you're an engineer, and I've been an engineer before, and I hate studying, so I assume you should. Is this working? Hi, besties. We're back. Are we back? We'll be back when I find the pen. Here it is. Okay. So, the rest of today's lesson involves no complicated mathematics. There is an integral, but I already solved it. Okay? The entire rest of today's lesson is just learning new formulas and new points. Oh, come on. All right. But as the course goes on, more and more of the lecture will be like what we've just done. Okay? Like in week 3, which I'm still writing because I'm catastrophically behind, right? We can all relate. In week 3, the first lesson is literally just Tom derives 2 things, right? And because Tom derives 2 things because you must be able to derive them in the exam, derives 2 things. Not Tom derives 2 things because he's an egotistical wanker. But remember how we had the definition of E last time? E equaled, okay, yes, also, but wrong E. E equals F over Q. Well, what about this? It's the same, right? This one is the more useful arrangement because in the majority of cases, such as for the example with the rod that we just did, we find the electric field first, and then we can find the force. Okay? So what you would do is you would take the charge including the sign in coulombs. You would multiply it in by the electric field, and this could be in x, y, and z, right? You could do the x force, the y force, the z force. The best part about all these vectors is you can always treat x, y, and z as independent. You can always do that. That's how Cartesian coordinates work. Thank you, Descartes. The same person as I think, therefore I am, by the way. I know. Someone thought, certainly not me. And so you just literally multiply Q in with E. So you'll have E as some big wobbly-bumbly equation. That'll be part 2 of the question. Then part 3 is like, all right, what's F? You literally just slap Q on there. That's it. It's done. It's pretty easy. All right? What? Where's the picture? What? Hey, what? The picture's in the slides here. What? Okay, well, in the slide that I printed out, it was there. But don't worry, because it assumes that we solved the integral that I solved earlier. It assumes we solved that big question, right? It was a rod, and we had the charge. It was here, and we had this length, and we had no. But I don't know why it screwed up, but it did. It even, like, it's a subset of its own. I don't know how that happened. Again, technology. But that doesn't matter, all right? The important part is, if you found E, you just slap Q on it. Then you got F. That's how it goes. Just smash them together. All right. So now we have another question. This, I'm going to be honest with you, is a learning outcome. That's about it. So I want you to think, what forces act on a droplet in a, has anyone know Millikan's oil drop? Yep. So can anyone describe Millikan's oil drop to us? What is it? Oh, it was a spoilers for everyone, right? So we have a object, and essentially it is charged. And it's in an electric field, but it's also in space. And there are some forces acting on it. It should be a word cloud. Is anyone able to open it? Did anyone go on the poll? Anyone submit anything? I've got 0 responses. Oh, we got 1 response. Thank you. Right, remember, echopoll.au/physicsgang. This does not show up in an assessment. I'll level with you, but it does show up in the first lab from term 3 onwards. Not this term, because I haven't fixed it yet. So, sorry. I currently haven't gotten it so that you can't jab your own eyes out. So, this is just a little vibe, right? We determine the charge on an electron by measuring the charge of an absolute shit ton of droplets of oil, and then realizing that each of those charges has to be quantized according to the same metric. So what Millikan and Fletcher, his PhD student that everyone misses out on, did was they used a complicated force balance to measure the charge of this object because, chat question. Physics gang. Oh, thank you. Right? Because swimming. The charge, so the forces that act on this will be something like gravity acting down, and then they'll put it in an electric field, and they'll probably have QE acting up, right? And so how they measure the charge of this droplet is they measure its mass, and then they measure the electric field that they put in, and they tune the electric field until it floats. And once it floats, you can find its charge. Do that 200,000 times, exaggeration, smaller number, and look at all the different Qs. And that's how you figure out the charge on an electron. Now, it is actually substantially more complicated than that. And if some idiot hadn't ruined the Millikan lab, which was supposed to be the week 2 lab, then you would experience those complications. But some little idiot hasn't gotten the digital cameras working for it yet, and it's impossible to do by eye, apparently. I did it by eye fine on one where I had to work 4 different things at once, but it's too hard for first years. I'm just goated like that. So I had this entire slide literally Millikan ramble. We're going to skip Millikan ramble for time. All right. I hope you can agree. because we have more important things. All right? And I want to keep it to things that matter for specifically the things that you get grades on. Right? Hello? Come on in. Come on, let's go. Where you guys going? Anyway, so who earlier said that the reason why the charges go along the edge is because we can't have any charges in the middle? Was it you? Was it one of you guys?
No, it's not me.
Was it James?
Yeah.
Yeah? All right, cool. All right, hang on. I forgot your name. Sid, that's right. All right.
That's fine. It's because to minimize the electric potential energy.
That's also true, right? And we'll get to electric potential energy next week when we define it, right? It's all this. The best part about a lot of this stuff is that you can use like 5 different principles to prove the exact same thing. It's like English class, right? You can use whatever interpretation you want, right? Now, the thing is, and this is actually really, really important, the electric field inside a conductor must be 0. It is always 0, and what this means is that charges move around to ensure that this is true. Okay? That's why, for example, when you have a charged conductor just chilling by itself and you slap a bunch of charges on there, they distribute around the edge because there can never be charge in the middle if that would cause there to be an electric field in the middle of a conductor, not an insulator. Remember, insulators, they have their own bullshit. And so what we might then consider is what happens if you take this charged sphere and you apply an electric field to it. The charges must move in order to neutralize the electric field within the conductor. Because the electric field inside a conductor must always be 0, even if you are applying an external field. Okay? So, I'm going to freeze this question, because the next one has a question. Let's go freeze. I want you to imagine we have a neutral conducting sphere. Neutral because it's got equal pluses and minuses, and I counted this time, right? And we apply the following electric field. And I want you to think, and I'm really sorry for how this looks, how do the charges distribute themselves? What happens? Again, we go to echopole.au. I feel like I'm like shilling for Echopole, you know? And then the code is physics gang. Why is the parking inspector here? Oh, he's going to the toilet. I really shouldn't have said that on the record. I can't edit that out either. All right. I want you to think, what's going to happen to the charges? Now think in terms of each positive charge. What will it do? It will experience an electric field. Where will it go if it is allowed to move freely? Or you can think, how should the charges be set up to make sure the electric field inside the conductor is 0? Both of those lines of thinking should get you the same answer, because that's how physics is supposed to work, right? Are we ready? So we've either got no change, or B, they split up, just go everywhere, or C, they polarize one way, or D, they polarize the other way. Now, I'll give you a hint, C or D. It's one of the two. They do polarize. Oh, I wrote it here, look at me, I'm so good. I wrote it down there, I'm the goat. I just can't read. Whoa! Positive charges move to the right, and negative charges move to the left. That's entirely correct. That's entirely correct, nice work. Of course, because the positive charges, they're going to follow that electric field to the right. And the negative charges, they're going to F you, I won't do what you tell me, to the other way. Right? I have that song in my head, you know, the F you, I won't do what you tell me song. That's every time I think of a negative electric field or a negative charge. Now we can also think, right? I'm going to unfreeze. Right? Here we go. We can also think of it in terms of neutralizing the electric field. So let's say we have an electric field like this. This is our external electric field. If I want to make a field to cancel that field, which way should it point? The other way. So what we want is to make a field that points the other way. We want to make a field that points this way inside the conductor. Now, fields, they point from where to where? Positive to negative. So we have to set up positive charges over here and negative charges on the left to make our own field to cancel out the external field. Alternatively, the positive charges get pushed to the right, the negative charges get pushed to the left. Both explanations yield identical results. We could even talk about minimizing electric potential energy, right? We don't even know what that is yet, but we get the same answer, all right? And it doesn't matter what your head canon is, as long as you get the correct results. Okay, you can think of it how you want, because the outcome is the same. What's up? No sweat. We just got to our break. JK, we just finished our break. Right. Question. It is similar to Lenz's law, but it's got nothing to do with Lenz's law. But it's the same vibe, right? Same vibe as Lenz's law. I love Lenz's law. Lenz's law to me is like the grandparent law, because like nothing must ever happen, everything must stay the same. What's up?
Don't the charges on the surface affect the inside of the conductor?
Yes. So in reality, it is far more complicated than just to say, oh, all the positive charges go over here, and oh, all the negative charges go over here.
No, I mean, why is inside the conductor the electric field is zero?
Why is the electric field zero inside a conductor? That is interesting. For now, we must accept that it is true. The answer is because the electric potential inside a conductor is zero, and that means the field is zero. Well, actually, okay, better explanation. Does anyone know the difference between static or steady state and transient, those words? Steady state is the equilibrium and transient is not. If there was an electric field inside the conductor, the charges would be moving. And we, in this course, this is a very good question, only ever deal with steady states. So we only ever deal with the waited for a long time, everything has settled condition. And by definition, everything can only be settled when the charges don't move anymore. And in a conductor, the charges will only stop moving when there's no electric field. And so by definition, every problem we ever see must have no electric field inside a conductor, because we only ever deal with the steady equilibrium. That is a very good question. That's a very good question. And I'm very satisfied that I knew the answer. But that's, I was thinking that actually for lesson 2, because we were talking about all these moving charges we'll do later. Anyway, okay. So, water break. That's a lot of stuff. Don't worry. We're going to do 2 things. We're going to learn a new formula related to dipoles, because it's assessed. And then we're going to learn about Gauss's law, because it's really important. We don't do any Gauss's law today, right? We're doing Gauss's law next week. But today we're going to learn the terms in it, all right? And then next week we're going to do some integrals again, all right? Does anyone watch Jujutsu Kaisen?
Yes.
All right, so Gauss's law is like domain expansion, all right? And we're going to get there. It's exactly like domain expansion. It's the best. Anyway, first of all, dipole, okay? So the first thing to recall is that a dipole is just 2 equal and opposite charges. Oh, yellow was the better color, wasn't it? Hang on, we'll go back to yellow. Does anyone read any Ted Hughes poetry? No? Good. He's a jerk. He's Sylvia Plath's husband. Anyway, I'm not going to get into poetry. So, a dipole is 2 equal and opposite charges. 2 houses alike in digging. No, that's Shakespeare. And they have, what we say D here, is the vector, the displacement vector, going from the negative charge to the positive charge. We defined it this way because we had to pick one way or the other, and this is the way that was picked by convention. That's it. There's no other reason. This is just the way that it was chosen to refer to dipole. Oh, there's a question in the chat? Fuck yeah. I mean, hell yeah. All right. What are positive charges made out of? Holes. If there's a strong enough electric field, would it be possible to have non-zero electric field inside a conductor? I reckon so, but it's not here. Not for our class, but absolutely. Because, no, I'm saving myself from this ramble. I've got a ramble saved up for that. We'll go through it, all right? Whoa, nonlinear optics is my favorite field, but we'll get, no, focus. I get too excited about physics. Anyway, so D with a hat was the displacement vector going from negative to positive, and the parameter that mattered of a dipole, I like to call it the descriptive parameter. The parameter used to describe a dipole was P. P for pole? I don't know. I don't know why it's P. It's too many letters. But the other way around, there's not enough letters. We keep reusing them, right? Just like how we reuse asbestos in our mulch. So, those of you watching this 10 years in the future, hopefully you don't have cancer. I visited the mulch yesterday. The dipole moment is P is equal to Q times D, right? D being that vector, so the dipole moment also points this way, okay? What happens when I put it in an electric field? I want you to ask, how does it move? Just, yeah. Oh, love the chat. Thank you, chat. You are the best. Can I get an F in the chat? No, W in the chat. There we go. Anyway, how does it move? Anyone? Any guesses? What's going to happen to it? Keep in mind, we have to assume the two dipole charges are somehow attached, like a water molecule, right? They can't just leave, all right? Question? Yes. Yeah. James, you going to say the same thing? Yeah. It's not going to move left. It's not going to move right because this one's going to experience a force that way. This one's going to experience a force that way. If we assume the dipole cannot separate, like a water molecule, those two H's and the O, they can't separate, then there cannot be linear motion. So we can only get rotational motion, all right? Because the dipole, remember, is by definition balanced on both sides. So there can never be linear motion of a dipole under an electric field unless you like kick it or something, right? Unless you provide some more force. And so that is an important fact. So important that it's in a big field, big red thing. A dipole experiences no net force in an electric field. It only experiences a net torque, so it's just going to spin. And it's not going to spin that much, right? Because all it's going to do is it's going to line up with the electric field. And we're going to ignore its momentum, so we'll just say it stops there, right? Of course, there's momentum considerations, but that's too much. That's too much for us. I'm not going to do it. Don't worry about it, all right? It only has a net torque. What's torque? Oh, F cross R, yeah. It's the spinny force. Bestie, we do torque in your course. Yeah, woo! Guys, gonna be more hype. So, are we gonna derive the torque today? No! Yes? Do you mean like it'll move this down and this up? Or, I mean, yes, that's exactly what's going to happen. But I'm treating these as point charges, sorry. So there's no distributions that can happen, but what's going to happen is, yeah, it's gonna turn out like that. But the force that makes it do that is the torque, right? So that's what we'll say, right? Because the whole thing doesn't end up moving left or moving right or moving up or moving down. All it does is it was this way, and now it's this way. And then it stops. It just lines up with the electric field, and then it stops.
Why does it stop? It's supposed to keep rotating.
Correct, because it has momentum, right? Because it's too much for us. Of course it would keep going, right? But we assume it has no momentum, and therefore it stops as soon as the force is zero. Why? Because it's too much if we put momentum in it. But absolutely we should, but we're not gonna, right? And remember, that was one of the core components of this course, understand limitations, right? That's a limitation. We should consider the momentum. We don't, right? Now, I've got many rambles about that. So before we continue, we need to talk about torque, right? And that is torque directions, okay? We actually like to call torque positive and negative. I know. So you use your right hand grip rule, okay? And if so if it spins this way, right? I want you to take your hand and I want you to make your right hand grip in the same way that I spun the thing. Your thumb's pointing at you, right? So that's out of the page, that way. And into the page would be the other way, clockwise, right? Yeah? Now, even worse, out of the page is positive. So it's plus torque along the z-axis. And into the page is negative. Do we ever have to really do this? Probably not. All right? But when you are doing practice questions on it, if they start to ask you about directions, keep those conventions in mind. That we use the right-hand grip rule to figure out into or out of the page, and out of the page is positive, typically speaking. Okay? It gets complicated. Who's doing mechanical engineering here? One of us. It's going to show up in MAN 1300. I know this because I did mechanical engineering at this university, and I only failed 2 courses. So, they were both maths, so it's fine. Statistical mechanics. Oh, we got chat. PogChamp. Big. Oh, okay. Just chat's just popping off. All right, good. It's good to have the chat popping off a little. Someone asked, can they watch these lectures live? The answer is no, because I don't know how to make it work. The actual answer is no, because it's not possible to make it work. But, you know, sad. We used to do these Zoom live, but it was real complicated. Anyway. Torque on a dipole. Again, this is just a formula I'm going to show you because I want to focus on the things I've deemed more important, very selfishly. Shit. I mean, oh, maybe it was far enough away that it didn't hear me that time. Yeah. You're doing a lat exercise, bro. Dude, lats are always the hardest. No cap. I can't wait till lecturing is over, then I can go to the gym again. So the torque, and we could have derived it, but we didn't because you never get assessed on the derivation, all right, and we're being strategic here, is the dipole moment, that's the word, times E with some form of direction. So it's technically the dipole moment cross E, cross product. It's a vector cross product. If you don't know what that is, don't worry about it. Don't worry about it. It's fine. Don't have to worry about it. It is Q, D, E, sine theta, and I've put absolute values on D and E. I'm saying don't worry about the direction. Okay? Q, D, E, sine theta, where theta is the angle between D and E. Okay? Now you might think, from that formula, how do I tell if it's clockwise or counterclockwise? And the answer is, you don't from that formula. Correct. And so, here is where we run into one of the key problems in physics. If you took my Fundamentals of Physics course, you would know that I really hate rigorous mathematics and I really love vibe in it. But as soon as you touch second year, that no longer works because we lack the ability to look at something and tell how it's rotating. This, we can look at and tell how it's rotating, right? But it's possible that we'll get to some sort of stage where we will not be able to determine direction simply by looking at a problem. And in that case, we have to be rigorous. And that means we have to make sure we define theta the correct way if we choose to use theta to figure out our direction. So if, and only if, you decide that theta is the direction between the P vector and the E vector, right? The P in the electric field. So notice it's a very slightly different theta to what I did last time. The sign is the same, but the way it trends is different, all right? Then, and only then, does this formula with direction work, right? Keeping in mind that sine theta can be 0 through 180. Sorry, so theta can be 0 through 180, so sine theta can be from -1 to 1, right? So keep that in mind. Now, my recommendation is literally just look at the problem. Just do QDE sine theta for the magnitude and look at it and go, it's either clockwise or anticlockwise. Okay, that's my recommendation, and that will serve you well enough if you never, ever, ever go to second year physics. But if you go to second year physics, you must be rigorous, all right? And this is what I mean by understand limitations. I make decisions based on what will help you the most now, and I may be disadvantaging you in the future. right? And I'm making that choice. So just keep that in mind. If you're an electrical engineer, you're fine. Don't worry about it. All right, everything's happy. We're fine. No, it's a serious thing. This is what I struggled with the most in deciding what to do. Because we could spend a lot more time and do everything the right way. But then that would, in my opinion, be a waste of your time specifically for this course, right? And it's not a decision I'm terribly happy with having to make, right? But it's just how I've chosen to do things. And that's why I put understand limitations as one of the most important aspects of this course, because you have to understand all the shortcuts I'm making and when they stop working, so you don't go into second year and go, well, Tom told me it was this, and everyone's going to be like, Tom, what are you teaching these kids? So, what I want to ask you, do you notice the difference between these two pictures? They're on the opposite sides, right? Now, do they experience different magnitudes of torque? No, they don't. Angle is the same, isn't it? But these two are unequivocally different. How? How are they different? Direction of the torque, yes, and? Well, maybe on the... Sorry? Very good. What were you about to say? Same thing. How much they're going to move. So perhaps the potential that they have, or some form of maybe potential energy, right? Because you're right. All of these, assuming no momentum, of course, are going to align perfectly with the electric field and then stop. For this first one, it's going to go down here. It's going to like become horizontal this way. It's going to move a little bit. It's going to move like theta. This one's moving all the way over there. This one's moving all the way over there, right? Because the negative charge wants to be on the right-hand side, and the positive charge wants to be on the left-hand side. They're going to experience forces following. Yes?
So like as the dipole aligns with the field,
yes.
the potential becomes 0?
Correct. Well, it depends on how we define 0, but we will define 0 that way. All right? So yes, right? And that's actually a really good point because we're going to talk about that next week. Where do we find potential as 0, right? But these two are different because they're going to move different amounts. So they must have different potential energies. To find the potential energy, what we could do, but I did for you, is calculate the work done. Now I want to let you know that the work done on a linear system was integral of the force times the displacement, and the work done for a rotational system is the integral of torque times the angle. How does the math and physics describe the non-stable equilibrium? Second year. And these are all interesting questions that I would love to ramble on but won't for time. But unstable and stable equilibrium points are discussed in second year Lagrangian mechanics. It's a really interesting topic. Tarek. For what I'm specifically talking about is taking this formula and converting it to a rotational formula for torque. But you absolutely could do the potential energy of this charge as it moves this distance and do the potential energy of this charge as it moves this distance. You'd get the exact same answer, right? That's actually not... Maybe I should have derived it both ways and showed that they're the same. That's a very good question, Tarek. But you're right. So you could have actually done it linearly, right? You could have taken one charge, it moves this much. Second charge, it moves that much, right? That absolutely works. The reason I'm doing it with the integral of torque is literally because that's how we do it in the assessments here, right? But you're absolutely right. You get the same answer if you simply considered the... Technically, you'd have to consider only the motion against or with the electric field, so there'd be some more angular considerations, so it'd be slightly more annoying, but you get the same answer. And that answer for the work done moving a dipole between angles 0 and theta is this, okay? Now our definition is when theta equals 0, potential energy is 0, right? Oh, hang on. I haven't done the potential energy yet. Hang on. There we go. Sorry. If we assume, this is the important slide, right? If we assume the potential energy is 0 when it's horizontally aligned in the stable equilibrium point, because as someone points out, technically it's stable when it's exactly 180 as well, right? Because technically the forces are holding it still, technically, right? It's an unstable equilibrium, but it's an equilibrium. Anyway, if we assume the potential energy is equal to 0 at theta equals 0, then the potential energy of a dipole is simply given by this. All right? It's just that formula. So when theta equals 0, the potential energy is PE times 1 minus cos of 0. What's cos of 0? 1. So what's 1 minus 1? 0. So what's anything times 0? 0. If theta equals 180, which is the maximum possible deviation it can be from equilibrium, because, you know, if it goes over 180, it loops back around. If theta equals 180, what's cos of 180? Minus 1. What's 1 minus minus 1? It's 2. So it's the biggest possible number, right? And then if theta equals 90, then you've got 1, because it's 1 minus 0, right? That's how I know I did it the right way, because I checked that the biggest number is at the biggest angle. And now, finally.
Can I think of something before we
Go ahead. Yeah, I'll go back.
How do you measure the theta?
Theta is defined as the angle between, not the angle between screams, sorry. The angle between the D vector and the E vector. So it's explicitly the angle between whatever the electric field is and whatever the dipole moment is, right? So when theta equals 0, when theta equals 0, one more time. When theta equals 0, right, it's defined as the dipole moment and the electric field being in the same direction, the exact same direction. And theta equals 180 is defined as the electric field and the dipole moment being exact opposite directions. That's our definition of theta, right? If you get a different theta in your exam, you have to make it the right theta. And that is another reason why the dipole moment was defined that way, right? If the dipole moment was defined as pointing the other way, pointing from positive to negative, then this formula would be slightly reversed somehow, right? I don't know how, I mean, we could figure it out, it's pretty easy, but I'm not going to do it on the spot because I'll make a mistake and everyone will think I'm a dumbass, right? Never do any derivations live, all right? This is my recommendation to you. Always give yourself infinite number of time.
Thank you.
Yes. Okay, now we do a new thing. That's an old guy. That's not the new thing, don't worry. We can get up, do a little shake, you know, or not. Woo, do some exercises, do some cable crosses, you know, get on it. It's almost the weekend, which means it's almost time to actually go to the gym again. The best part about only being able to go to the gym 2 days a week is that I only do, I skip leg day every single week.
Oh, they're going to do 2 leg days.
No, like legitimately, I have to skip leg days or I stop fitting in my clothes. It's an unfortunate, I'm too jacked. That's a joke, of course. All right, new thing, no thinking. Okay, little bit of thinking. No math, a little bit of math. No integral. Okay, new thing, no integral. Now, this new thing is going to save us so much goddamn time and effort. All right? So I know it's like, Tom, why are you teaching us a new thing? And it's to avoid work. All right? There is a lecturer here who I won't name, even though I'm saying a positive thing about them because it's on the record. And I was talking to them, and I'm like, I love Gauss's law. And they're like, I love it. Because in physics, it's all about minimizing effort, right? This person is a theoretical physicist, and being a good physicist is looking at a problem and going, how can I get away with doing this with the least possible amount of effort, right? That's legitimately physics, like least possible mathematical effort, right? And that's what we're going to learn. Because we're going to be, next lesson, doing the electric field due to some complicated bullcrap shape. And how would we do it according to our normal system? Well, we know that the charges are distributed all along the surface of the object, wouldn't we? Including the bottom and including the sides. And so we have to take, every single possible DQ from all the different positions. It's not going to work. Okay, you could do it. You absolutely could do it. And you would suffer, right? Why would you do it that way? So what we're going to do is we're going to learn a better method for finding the electric field due to shapes. And you might think, well, then why the hell did we just learn the old method? And the answer is because you have to suffer a little so that you understand what it means to be saved. That's very preacher of me, isn't it? So, we're going to talk about electric flux. Now, this is the point at which I broke my computer, so I'm going to try my best for a drawing, right? Electric flux. Like, let's say you got an electric field, right? Would it make sense to you that if I put a small object in that electric field versus putting a big object in that electric field, the big object experiences more electric field? Right? It's bigger in the same field. It's got more field going through it, is the idea. Now, hello? They're not coming in. I'm sad. Right? That's what we call electric flux. It's the amount of electric field going through an area. Now, we have a formula for it later, all right? But in reality, it's just the total electric fieldness going through something, and it's proportional to how much electric field there is, so the electric field strength, and how big the area is you're talking about, and vectors. And I'm sorry for the vectors. It's technically like the electric field is electric flux is the measure of the electric field going through a surface. Did everyone do physics in high school? All right, everyone nodded their head. Wink. And so it's basically magnetic flux, but it's the electric version. All right? Magnetic flux is the magnetic version of electric flux. And so there you go. You got both definitions. Right? It's the, look, I'll show you a picture. Right? It's the amount of electric field going through a system. Now, importantly, every single formula that I'm bringing up that is not in a red box is not a relevant formula. I'm just using it as examples, okay? So, we could define for some shape, right? Do you ever remember when they did motor effect and they had the coil rotating through the magnetic field? This is exactly the same stuff. Fuck. The only new symbol I want you to see is phi E. That's electric flux, okay? And in the common sense, it is electric field times area with some sort of reduction for the understanding that if the area and the electric field are perpendicular, then that's maximum flux. And if the area and the electric field are parallel, then that's minimum flux. Now, importantly, the way we mathematically describe that is to say it's cos theta, where theta is the angle between the electric field and the normal of the area. And that's why we did it that way in high school, with the normal of the area instead of the angle with the coil. Right? The normal of the area is the vector that is at right angles to that area. And if you're like, Tom, what the hell are you talking about? Don't worry. It's not a big important slide. Okay? The emphasis here is that it's to do with the size of the electric field, the size of the area, and some angular consideration about their relative orientations. That is the important point. Because, it's actually way harder. Now, I promise you, when we actually do Gauss's law, it's piss easy. But we must learn Gauss's law first. And Gauss's law involves area integrals. Will we do one? No, of course not. But we will look at one and go, okay, and then we won't do it, all right? In second year, you absolutely will do it, which is why I'm teaching you the proper form. Technically, the electric flux through a surface for which E is not constant, so E might vary at different parts along the surface, is the integral of E dot dA, where E is the field at a particular point of the area, A is that area element, so we'd integrate like an area integral, and dot is dot product. Okay? Now, if you don't know what a vector dot product is, I'd recommend watching a couple of videos on it. The main reason is because I couldn't give you a good explanation in the amount of time that we have, all right? But I would recommend for next week knowing what a dot product is, okay? It's important, and I don't have the capacity to teach it, and also it's part of the assumed knowledge of the course. I finally got to use that cop-out for once in my life. So dA is where you should shit yourself, all right? Because earlier we did an integral, right? We did an integral dx, right? Where we just did an integral along one dimension. Now what we're going to have to do is we're not only going to have to take an area and break it down into little area elements. We might have to take those area elements and make it dx, dy, and integrate in 2 dimensions. Not only that, but we have to consider the direction of that area, which is normal to that area. It's pointing out of the surface. And we're going to have to do an integral like that for the most simple case you've ever seen in your life. All right? I emphasize, this is going to get insanely easy. We are going to do circles and rectangles. We are not going to do anything complicated. But there's no way to express it mathematically without expressing it in its full glory. So that's what we're doing, okay? We're going to have to next term, and by next term I mean next week, convert area elements to some other elements, like dx, dy. This involves variable substitution and dot products. I'd recommend getting on top of it because it's going to be assessed in week 3. You can ask me about it. I will help you, just not in the time that we have today, okay? And I'm aware that it's like this is maybe the first course where there's actual assumed knowledge that I don't have time to teach you. But the solving strategy for these problems, which we're not going to do today, right? We're going to start next week on them. So I just want you to be scared this week, right? Is 1, to know that they give you easy questions. Okay? All the questions are piss easy. Spheres, circles, rectangles. These were in harmony before the Fire Nation attacked. No, those are the ones you're going to do. Step 2 is to convert dA into some integrable function. The only 2 ways you ever do it, you take an area element, you make it dx, dy. Or you take an area element and you make it a circle, so you're just doing an integral along dr. That's it. Those are the only 2 ways you ever do it. All right? And again, that's still some maths that you've got to get your head around, but that's all it ever is. Then you find E dot dA in terms of the variables given. Ideally, it means you get to ignore a lot of components because it's E dot dA, right? And there will be portions of the surface that are perpendicular to E, and E dot dA, if A is perpendicular to E, is 0. So the dot actually is clutch. It makes the integral way easier because it lets you ignore basically every component that you don't like, because that's exactly what we're going to do, right? What we'll actually see is we'll have this complicated shape and we'll go, all right, literally only this portion of it matters. Like we'll have like a shape like this, and we'll go, all right, the circle matters, nothing else matters, integral of the area of a circle. And you know what? Most of the time the electric field is constant, right? So most of the time it's literally electric field times area, all right? There is just the occasional circumstance in which it's not constant. And also, I would be a terrible person if I taught you Gauss's law in a form that only accommodates constant electric field. So I'm teaching you the complicated one. All right? This is the most complicated one we will ever see in terms of integrals. All right? I stole it from the assessment and then changed it a little. All right? Find the flux phi e equals integral E dot dA for this rectangle where we have a field going into the page, right? I've got the field going into the page. So what we're going to do, we're going to look at E, and we're going to realize, well, we could say it only varies with x, so we could just treat the A as a constant, so the y as a constant if we want, but I'll do it properly, right? I'm going to walk a little faster just because I want to make sure we get through it. So what we're going to do is we're going to say, all right, well, dA, that's just dx dy. Don't come for me, variable substitution purists. Okay, it's that. All right, we're just deciding that it is. Okay? So dA is simply dx dy. And E is 1.23 x squared. So phi is equal to the integral in both x and y, hello, of 1.23x squared dx dy. We could do that integral, couldn't we? We just need to know our limits. I've said it goes from x equals 0 to x equals 10. That's this distance here. So that's x equals 0 to x equals 10. And it goes from y equals 0 to y equals 5. And that's it. It's just that integral, right? You take the function for e, you put it in there. You take dA and you split it into shit you could integrate. And then you apply the appropriate limits. And it literally just solves like this. Now, again, you might think, Tom, I don't know how I'm going to do that. Take the practice quizzes and just take them slowly. Just do it methodically. And just ask me. Don't forget, we got a revision session on Tuesday, week 3, right? Where I may go through the specific exam questions if you ask them. But anyway, we do that, right? The integral with respect to y, because there's no y in this, that's just going to come out as 5, right? So it's going to be 5 times the integral between x equals 0 and x equals 10 of 1.23 x squared dx. And that integral is fairly easy, right? That's going to be 5. What have I done? God damn it. It's going to be 5 times 1.223 times x cubed over 3 between 0 and 10. And, you know, the 0 is 0. So it's going to come out as 5 times 1.23 times 1,000 over 3. And it's whatever that number is, right? The integrals, that's the most complicated one you actually do, okay? Constant, it's a function of e over a rectangle. That's the most complicated integral you do. You do see worse shapes, but they are constant e, okay? But I want you to understand that you could see some horrifying shapes. We won't, but be warned of the horrors that await behind the curtain of second-year physics. Okay, so here's another rule. Flux go in, flux go out. Right? I got to make sure I hit these, so we're going to go slightly fast. For any object that is inside a constant electric field, the total flux is 0. Because any flux that goes in through one side has to come out the other side. So if you add all of the fluxes together, it would sum to 0, keeping in mind that direction is important, right? So you could specify into the surface as positive and out of the surface as negative, or the other way around, right? Your choice. But they would add up to 0. Any flux that goes in must come out, assuming, of course, that we were in a constant electric field, or more specifically, assuming there wasn't any charge inside it. Because flux comes from charge, because electric field comes from charge. If there's no charge inside it, whatever flux goes in must come out. That is a core concept. Very useful for problems. Here's an example, right? And it is another response question, but I just want you to call out, because we don't have time. How would you solve it? This, I will tell you the area of side A is 3 meters cubed, and the electric field strength is 2.3 newtons per coulomb. So what's the flux going through side A? If it's E times A, if we remember.
6.9.
It's, yeah, oh, whoops. It's 3 times 2.3. That's the flux going in this side, right? Oh, I mean, I know the arrows point the other way, but we can choose in and out as whichever side we want, right? So, that's the flux going inside A. And let us assume that this shape only has one other side, this weird shaped side, side B. What's the flux through side B? It's negative that. Because it has to be. Any flux that goes in has to come out, which means just pick the side that's easier to calculate and do it that way, right? Because it has to add to 0. Now the final thing before I get kicked out. Oh, woo! One person got it right. Nice work, one person. James, I assume, from your happiness. Unless there's a charge inside, okay? Flux go in, flux come out, unless something flux it up, which, ooh, right? Didn't swear that time technically, right? Because if there's a charge inside, the flux doesn't cancel out anymore, right? Can you imagine, like this case, for example? You take an object and you put a little charge in it, right? Now, we're not talking about whether or not this object is a conductor or a non-conductor. Don't think about that yet, all right? But you take this object and you put a charge in it. Well, we know that the net flux is not going to be 0. But we also know that any flux that came from outside must pass outside and be cancelled out. And what we can therefore conclude is that if there was a charge inside this surface, the net flux, which is all the flux going in minus all the flux going out, or the other way around, all the flux going out minus all the flux going in, the net flux must depend only on the charge inside the object, because any external source of flux has to go in and then come out. And that is Gauss's law, the law we will be using next week, that the net flux going through any surface, imaginary or not, is equal to the enclosed charge divided by epsilon naught. It is a very powerful formula, specifically for working out electric fields. Because I want you to imagine a case, let's say we have this sphere, right? Let's say we know the area of the sphere. And let's say we know that the electric field is constant throughout that area of the sphere. Then all of a sudden we can relate the area of the sphere to some sort of distance r, and we can figure out the electric field just using this formula. We're going to do this next week, okay? So this is Gauss's law. This is the most important part of the second half of the lesson, that the total electric flux, which can either be worked out yourself or done through this integral, it's always an easy integral, is equal to the charge enclosed in the surface divided by epsilon naught. That is Gauss's law, and that is what we will be using predominantly next week. I'll leave you on an easy example if you want, but that is class over. Thank you all so much for paying attention. Appreciate you all. Go home and do some practice questions, okay?